Okay, so we are presented with a problem here. So we have two metal spheres. Okay, one has a negative charge of 3 microcoulombs. Okay, very good question. 1 microcoulomb is equal 10 to the negative 6 coulombs. Okay, yeah, good question. So we can just change this right now. So negative 3 times 10 to the negative 6 coulombs. Good. And it's placed with a positive charge of 2 microcoulombs. Okay, so 2 times 10 to the negative 6 coulombs as well. Okay, the separation distance is 12 centimeters. Is centimeters a physics-friendly unit?
No.
No, so we'll just change that to meters. So
from between the center of the other one.
Yeah, you got it. So 12 centimeters is 0.12 meters. Okay, so here is the setup for our problem. Okay, so second part of it, the two spheres momentarily touch and then return to their original positions. Okay, so can anybody remind me of the law of conservation of charge?
Oh, the V equal now.
Yeah, so the charge going in must equal the charge going out, right? Law of conservation of charge. So we got charge in, so net charge in equals net charge out. Okay, so let's do our net charge in first. So if we have negative 3 microcoulombs and positive 2 microcoulombs, the net charge on that is negative 1. Negative 1 microcoulombs. And going out, okay, so no, okay? Because our net charge has to be conserved, right? So we have a net charge of negative 1 going in, so our charge going out must also be negative 1 microcoulombs, right? Because our net charge is negative 1 going in, it must be negative 1 going out.
Oh, but each sphere wouldn't necessarily have negative 3 and plus 2.
Exactly, right?
Equal negative 1.
Exactly, right? So good. So negative 1 microcoulombs going out. Okay, so this is our net charge of negative 1, and we have 2 spheres present, right? So we'll just divide that by 2. So divide by 2, which equals each sphere having a charge of negative 0.5 microcoulombs. All good there?
Wait, tell me what you did again.
Okay, so the law of conservation of charge says that the net charge going in must equal the net charge going out. Okay, so we were told that the one sphere has a charge of negative 3 microcoulombs and the second sphere has a charge of positive 2 microcoulombs. So negative 3 plus 2 is negative 1 microcoulomb. And then that that charge must be the same charge going out, right? But after they touch one another, those charges are going to to balance out, right?
Oh, okay. Oh, because it's positive, negative.
Yeah. Well, even if it was like 2 negatives, if you had a negative 5 charge and you had a negative 4 charge, after contact, they're both going to have the same charge,
Oh, okay.
right? They're going to kind of neutralize out.
So it'd be 4.5.
In that case, it would be, yeah.
So in this case, it'll be 1.5, right?
Nope.
0.5 actually.
Yeah, negative 0.5, right? Yeah, because we have 2 spheres, we got to divide that negative 1 charge between the 2. So we'll get a negative 0.5 microcoulomb on each sphere. All good?
Dandy.
Awesome. Great questions, okay? So we know that Q1, so we're going to be using Coulomb's law here. So remember, Coulomb's law, Fe is equal to K times Q1 times Q2 divided by the separation distance squared.
And K is 8 point something times.
Yeah.
So it's something.
Yeah, exactly.
Is it 8.99 times 10 to negative 6?
Positive 9.
Okay.
Yeah, so Coulomb's law, K
Almost.
8.
is 8.99 times 10 to the 9
That's
Newtons.
from my sheet, right?
per, yeah it is, newtons per coulomb squared, or sorry I mixed that up, coulombs per meter squared, over, sorry, coulomb squared, newtons per meter squared, coulomb squared. Right, because then when you multiply that by Q and R, your meter squared and your coulombs squared will cancel, and you'll just be left with newtons.
That's your, the 8.9, hard is your K value, right?
Yes. Yeah, that is Coulomb's constant. Yeah. Very good. Okay, so the chart, so we know K is our constant. Q1 is going to be negative 0.5 microcoulombs. Q2 will also be negative 0.5 microcoulombs.
So will Q1 and Q2 always be the same?
No.
It's only the same because they touched, right?
Yeah, exactly. Yeah.
Ah.
Yeah, really good question and good inference there. Okay, very good. Yeah, sometimes you're gonna have like a negative 3 charge. You'll have a positive 2 charge, like our next
So if
problem.
they hadn't touched, it would be
Negative
minus
3 plus
3.
2.
Yeah, exactly. You bet. You got it. Okay, and then our R is 0.12 meters. Okay, and now we're just going to calculate the electrostatic force acting on the negative, or on the metal spheres. So Fe is equal to K times Q1 times Q2. Now make sure our units are in coulombs. Okay, not microcoulombs. Okay, so we have negative 0.5 times 10 to the negative 6 coulombs. And because those are the same charge, I'm just going to square that, okay? One also thing that I have to kind of get rid of, that negative, don't worry about the negative or positive charges, right? Because the value it's an absolute value, right? So we're going to put in our charges, and then after we get our answer, we'll ask ourselves, are they attractive forces or are they repulsive forces?
Could we just leave in the negative and then after we get the answer be like, oh, so this means it's repulsive?
Oh.
Yeah, you could. Just when we get into, like, when we have like 3 charged spheres in a system, it might just make it more challenging. So I would lean, like, you can do that, but I would lean towards just doing the absolute value and then just saying, is it attractive or repulsive? Okay? Good question.
So you have to put 10 to the negative 6?
Yes. And don't forget to square your denominator. Okay, so we will punch this into our calculator.
I just texted there and said this class is so nice without you.
Okay, so once you punch these into your calculator and you're careful with your brackets and your exponents and blah blah blah. So this is equal to 0.156 newtons. And because they both have a negative charge, what do negative charges do? Do they attract? No, they repel, right? So 0.156 newtons, repulsive.
Wait, say it again? They're both electrons. Oh no, they're both...
They're both negatively charged. so they will repel one another. Okay?
And also, why'd you put the absolute value of FE?
Because, well, that's how you're going to see it on your formula sheet,
Okay.
is it with the absolute value. And by doing it that way, you don't need to necessarily worry about if the charge is negative or positive, right? You can just put the charges in, and then after you calculate that, you will say if it's repulsive or attractive.
Okay. One more question. So if they don't touch and one's positive and one's negative, it's going to be attractive.
Yeah. Yes, you got
So
it.
before they touched, they were attractive.
Yep.
And then after they touched, they were all repulsive.
Yeah, because they both shared that net charge going up.
Makes
Yeah.
sense.
Yeah, really good questions, fellas.
We're on fire.
All good? Was everybody able to get to this point?
Yeah.
Yeah? Excellent. All right. Okay, so we did this yesterday, right? So we will do some more practice with this. We'll probably have like an entry slip question like this on Monday. Okay, because we're going to see a question like this on our chapter 10 quiz. Okay, so maybe put a star beside this. I can guarantee you there will be a quiz question on this one. Okay, I've been kind of dodging this slide a little bit for the last few days, but we've kind of been talking about it, right? So this is just going to show the relationships between two variables that we're graphing, right? So if it is a straight line, that is a linear relationship, or we can say that it is proportional, right? That's what we have. The electrostatic force is directly proportional to the product of the charges in the system. Okay, so this is what we see here. So that's linear relationship. We have quadratic relationships, so that's when we have like exponential increase, right? We have inverse relationships where it decreases like that, and then we have our inverse square relationships. We didn't see this nice of a shape in our graphs yesterday, right? But this is the relationship for the separation distance between charged objects and how the electrostatic force decreases as we increase that separation distance. Okay, next week, or maybe it'll be the week after, we're going to get into some curve straightening practices. So that'll be fun.
Nothing says fun like that.
Straightening curves, right? Yeah. Okay, so I'm just gonna jump through this. All right, excellent. So here's our next one. So now we have those spheres that have not touched. Okay, so they're just kind of hanging out. 3 small hollow spheres are hanging from left to right on insulated threads. So we're going to find the net electrostatic force on B. Okay, so let's look at B. If we wanted to draw a free body diagram for B, what would it be? So
What's a free body diagram?
a free body diagram, you would have done this in physics 20. This is just going to show all of the forces that are present, or that is acting on something.
Oh, yeah.
Yeah, right? So this is going to be B. Okay? What are the forces that are acting on B right now?
I feel like your pen is a lot thinner than it used to be.
It's
We were talking about this yesterday.
it depends if I'm on Smartboard or PowerPoint or not. We can talk about that, why it is. Can you see it okay with
That's
this?
Yeah.
You guys are all good? Okay. I've asked the Science 10 group a bunch because I feel like it doesn't like show up very well, but they say it's good enough.
Yeah, that's fine.
Cool. Okay, so back on topic. What are the forces acting on B right now?
2 and 2.
2 and 2 from what?
From east and west.
Okay, perfect. So we're going to have, and so negative and positive. So are those going to be repulsive or attractive forces? Perfect. Okay, so this is F net B. Sorry, I kind of Didn't draw enough space there. Okay. But this is positively charged and this is negatively charged. So B is going to be pulled towards C, right?
Wouldn't
So-
it pull towards A too though?
It sure would. Yeah. Perfect.
If
But
A
C
and
wouldn't be pulled towards B? Oh, because it goes from.
Positive to, yeah, right? So in this question, yeah, so you're definitely right. B is going to be attracted to A, and it's also going to be attracted to C, right?
but it's gonna be attracted more to A because it's closer.
Absolutely.
Good boy.
Absolutely. Well said. Okay?
Okay, but say if A and C were in fixed positions and they couldn't move,
Mm-hmm.
and B was put in 1.5 distance towards A and C, what would happen? It would just like stay in the middle.
If all the charges were the same and the separation distance was the
Yeah.
same, and we had the same charges like this, like positive, negative, positive, likely it would have a F net of 0, right? Because it'd be equal in both directions.
It's like it's neutral.
Exactly.
Okay.
Exactly. It's kind of just happy. Yeah. Okay, so free body diagram, we're good, right? What else did we draw that is going to cancel out anyways? What's holding it up? What's holding up the B? The string, right? So we have force of tension holding it up. And what's pulling it down? Yeah.
What's that?
This is just the force of tension
Do we need?
pulling it up. They will cancel out anyways, right? Because it's not moving.
No, that makes sense.
But I just wanted to finish the free body diagram. Okay, and then we would also say Fe, so the electrostatic force is going to be acting on B, and the electrostatic force is also going to
So
be.
would you add those up?
Yeah, you sure do. Kind of like what we were doing for momentum.
You wouldn't subtract them?
What, FT and FV?
No, you'd add FE and FE.
Yeah, but we're going to have to say one direction is positive and one direction is negative. Yeah. Okay? So I'm going to erase this just for the sake of my space. But you guys good if I erase the free body diagram?
Yeah.
Yeah, okay. And then I'm also going to do like another, not a free body diagram, but a free body diagram equation. Okay? So here we are calculating the net force on B. Okay, so I'm going to go F net B is equal to the force of C on B plus the force of A on B. Okay,
So then you do your Coulomb's law for A and C.
perfect.
Yeah.
Yeah, you got it. Okay, so we will find the force of C on B, and we'll find the force of A on B. Because they're in different directions, we're going to add some and subtract some, and then we'll find the net force acting on it. Okay? So-
do we have to use negatives for this one then?
Yes, we're gonna have to say one direction is negative and one direction is positive. You guys like right being positive, right?
Yeah.
Right positive and left negative, so I'll try to stick with that notation as much as we can.
I did not already.
Did you? Okay, that's fine too. Yeah, we'll get the same, hopefully we'll get the same number, just a different sign, right?
I'll switch it. It's not that hard.
Okay, so F C on B equals, so we're going to use our Coulomb's law again, so F E is equal to K Q1 Q2 over R squared. So F C on B, so that's going to be K times, what is the charge of C? That's going to be 2 microcoulombs. Yeah, which is 2 times 10 to the negative 6 coulombs. Good.
Can you just square that?
Yeah, you could,
Oh yeah.
for sure.
So couldn't it just be 10 to the negative 6, 10 to the negative 4 then? Should we square it or not?
No.
I did mine separately.
Like this? Or,
I did B.
Oh, it'd
I
be
did.
10 to the negative 8
I
then.
did C on B and I did A on
Oh, negative 12.
Yeah, that sounds better. Okay, and then our separation distance is 2 centimeters, which is 0.02 meters. Okay, so force of C on B, I got 89.9 newtons. And this is, we have a negative and a positive charge, so this will be attractive. So the force of C on B is that it is it's pulling B to the right with 89.9 newtons of force. Were we able to get that in our calculators? Yeah, great. So then we will do the same thing. I'm just gonna box this up so I don't lose it. And then let's do the same thing for force of A on B. So again, we're gonna have K. Charge of A is, and the charges are the same, so 2 times 10 to the negative 6. Oops, forgot my Coulomb there. Coulomb, 2 times 10 to the negative 6 Coulomb, divided by 0.01 meters. Squared. And we get a value, hopefully, of 359.6 newtons. And again, A and B have opposite charges. So this is an attractive force. Okay, and because A is attracting B to the left, we're going to say that this is negative. Okay, and last step here, we just need to find, because now that we know FC on B, or the force of C on B and the force of A on B, we can find F net B. So F net B is equal to, so FC on B was 89.9 newtons.
Wait, but why would, we're just doing direction now.
Plus negative 59.6 newtons. And then we get a value of negative 269.7 newtons. And we need to write this in sig digs. We have 2 sig digs, 2 sig digs. So we go negative 2.7 times 10 to the 2 newtons.
Can I take out the negative and put it towards A?
Okay, so if you wanted to rephrase your answer, if you just said F net B is 2.7 times 10 to the 2 newtons to the left.
So towards A.
Yeah, that would be fine too. All right. How do we feel? Good? Solid? Nice.
I like this one.
Yeah. The 1Ds. So this is one-dimensional example. Now we have a two-dimensional example.
No,
Okay. So we'll just do this one, and then I'll give to you guys some practice for the day, and then we'll call it. Probably gonna need an extra slide in this one. Okay. So we are calculating the net electrostatic force on A, so this one right here. given the separation distance between everything is 1 centimeter. Okay, so like we were doing on last question, we'll do F net A is equal to what? F net A is equal to the force of B on A plus the force of C on A. Okay, and again, we're going to be using Coulomb's law. Fe is equal to K Q1 Q2 over R squared. All right, so like we've been doing, let's find the force between the objects, right? We're just going to have to do this one at a time, right? So we'll do F, force of B on A first. So that is going to be K times the charge. So we have 3 times 10 to the negative 6 coulombs. That is the charge of B. And the charge of A is 5 times 10 to the negative 6 coulombs. Divided by 1 centimeter, which is 0.01 meter. And, well, you guys like up and right to be positive, so let's stick with that.
Isn't that the universal thing?
Yeah. But you guys like it more than I do.
Yeah.
I like honestly, I would probably say, if I was doing it, I would say that right and down are positive, but that's okay. It's just a negative sign, right? So that's all good. So we'll punch these into our calculator. And F B on A, I get is equal to 1,348.5 newtons. And B and A are both negative, so it's repulsive, right? Good. Okay, I'm just going to hang on to that one. And we will do the same for force of C on A.
But will C and A touch because they're attractive? So you have to do 1?
Will C and A touch because they're attractive?
Oh, never mind.
No, but is what's gonna happen, so because A is being repelled from B, right? So B is going to be pushing A this way, right?
And C is gonna be pulling A.
And C is gonna be pulling A downwards, for sure. So what do you think we're gonna be doing? Finding our resultant vector, right? Like we've been doing, yeah. Okay, good.
So we're going to use Pythagorean theorem in here?
Yep, you bet. A little bit of trig, a little bit of angle, simplifying. Good, that's what I like to hear. Okay, and then we'll do the same thing for A and C. So it's K, 5 times 10 to the negative 6, multiplied by 3 times 10 to the negative 6, divided by 0.01 meters squared. And I get 1348 attractive.
So you don't do the negatives in your calculations?
And would it be a negative 1,348?
Yeah, so you can include negatives in your calculations, and then, so you would just get a negative number suggesting that it would be attractive. If you get a positive number, it would be repulsive. But when you do that, it might be like if
FB on A, I would say negative 3 times 10 to the 6. Negative 6.
FB on it. Could you say that again? Sorry.
For calculating F B on A.
Okay,
Formula,
yeah.
A, and I do -3 times 10 to the -6 because it's a negative weight or whatever.
Right, so you would do -3 times -3, or times -5, right?
Yeah. Oh, I guess it would be the same.
And then you get a positive number, and then it would be repulsive, right? You can do that for sure. It just might be a little kind of tricky when you're doing your left and right and up and downs with your negative. So for myself, I thought it was easier to just kind of ignore the positive or negative on the charges, and then after I found the value, just say if
Find
it's
direction.
just find if it's attractive or repulsive. Yeah. Okay, good questions. Okay, so did we all get that value as
Will
well?
that be negative since it's down?
Okay, yeah, sure. For sure. Okay, so negative down, and that's being pushed to the right. Very good. Thank you, Micaiah. Okay, so now,
It doesn't even matter though.
Well, yeah.
yeah, it's going to be the ratio, right?
45
Yeah.
degrees.
So now that we have a horizontal component of the net force, right? And we also have a vertical component to the net force. So now we need to use our horizontal and our vertical component to find the resultant vector and the direction of that. Okay? So I'm just going to jump to this page, and here I will do our triangle. So we went to the right and down, right? So we had and so to find C, a squared plus b squared equals c squared. So c is equal to square root of a squared plus b squared.
Is net electrostatic force a vector or
Yeah, it sure is. So we need a magnitude and a direction.
because your answer does not have a direction?
On this one?
Yeah.
Well, let's fix that then. I have the answer with direction on here, just the one on there. Okay, so then we'll get a C value of 1907 newtons. Okay, so that's going to be our resultant vector, but we need to find the direction of it, right? So our theta is equal to tan inverse of the opposite divided by the adjacent. And because we have, well, this is essentially saying 1 over 1, right?
Yep.
There we go. A value of 45 degrees. So this is 45 degrees.
South of west.
Yeah.
Southwest.
South of west.
East.
South of east, that's better. Okay, so then we'll go FE net A is equal to, and we had how many? 1 sig dig at the beginning? 1, 3.
Well, technically, if you do it the same way that you did the other one, then it's 1.
It's -5.
Yeah, so 1907 newtons at 45 degrees east of south, or 45 degrees south of east.
Wait, so you don't do sig days?
Yeah, sorry.
2 times 10 to the 3 newtons 45.
We got 3, 1, 1. So really we should give our answer in 1 sig dig. So
It's 2.
2 times 10 to the 3 newtons.
And you wouldn't do sig days for the angle?
Yeah, you would too. Sorry, this was a bad example for sig digs. So, yeah. In the future, like on a quiz or something like that, you would get like 2 sig digs.
How would you do sig digs for angles? You just do
Just like
5 times 10 to the.
yeah, exact 5 times 10 to the 1, right? So it's not very accurate. That's yeah. So if when you're given like a quiz or a test question, I'll make sure that you have like at least 2 sig digs. So because that's not very accurate, right? It's like 5 times 10 to the 1. It's like 50 degrees,
Yeah.
46, 49, right? Yeah, for sure. Thank you for grilling me on the sig digs. I appreciate that. So I was grilled with
My
physics
pleasure.
20s on that. So good. Okay, so let's leave it there for today, and I want you guys to have some practice on this. So I hope you guys brought your textbooks today.
1D.
Yeah, so we'll leave this 2D for tomorrow. So let's do some 1D practice today.
It's so easy.
So page 533. Actually go through the example that they have given, and because they'll actually like talk through it, and it's good for you guys to like compare what is going on and like have another explanation for it.